Alright, in this video we will learn how to solve polynomial inequalities such as these. Notice the greater than and less than or equal to sign. Well, for almost everything we do, by the way, this is number 7, it is helpful to get 0 on one side. So the first thing I would do is subtract 3 from both sides. Okay, if I do that, then I'm going to have x to the 4th power plus 7x to the 3rd power plus 12x squared minus 4x minus 16 is greater than 0. Okay? Now, I need the zeros of this polynomial. I need the x-intercept so I can do a nice little graph. Let's put this in the calculator and see how many zeros we can come up with using our TI-30 XS multi-view. So we hit the table button on the calculator. Just going to clear that guy out and start typing. So x to the 4th power plus 7x to the 3rd power. Alright, so here I've typed it all into the calculator. I always start at -10 because it rarely goes past that. So I'm scrolling down and I'm looking for zeros on the y side. Getting smaller and smaller. Alright, there's one. -4. Okay, so I'm just going to make a little list here. So I have my zeros. And the first one I found is -4. Okay. Anything else? There's another one at -2. Anything else? There's another one at 1. Okay? There should be a total of 4, alright, because the degree is 4. So there's one more out there. Okay, and it doesn't look like I'm going to get it off the calculator. That means I'm going to need to do synthetic division to find the 4th one. So that's what I'm going to do. Okay, so I'll just start with, you know what, I'm going to start with the 1. I started to go in order but because of OCD, but you know, the number 1 is just so easy. I can't resist the laziness factor. So I've got 1, 7, 12, -4, and -16. Okay, 1 times 1 is 1. That's 8. 8 times 1 is 8. That's 20. 1 times 20 is 20. That's 16. And 16 times 1 is 16. That's 0. Okay, I've got to keep going at least till I get down to a trinomial. So I've got another 0 here, so I'm going to use it. Let me switch to green. So I'm going to go ahead and use the 0 of -2. So I'll do -2 right here. Okay, 1 times -2 is -2. That's 6. Times -2 is -12. That's 8 times -2 is -16. That's 0. Now, I could turn this back into a trinomial, x squared plus 6x plus 8, and factor it. But you know what? I've got another 0 that I haven't used yet. So I think I'll just keep going and just keep using my zeros. So I'm going to use another 0, my 3rd 0 of -4. And see what happens. Okay, 1 times -4 is -4. That's 2. And 2 times -4 is -8. And that's 0. Okay, so I can use this last little polynomial to get the missing 0. So I've got all 3 of these. And now I have the polynomial x plus 2. Alright, that little polynomial x plus 2, you know if I take that x plus 2 and I set it equal to 0, that's going to give me x equals -2. Okay, so you know what's happening here. I'm getting x equals -2, but where have I seen that before? Oh yeah, look. -2 was right there. I already had -2. So that's the reason why it wasn't showing up on the calculator, is because the 0 of -2 is a double. Okay, so it looks like I only have 3 when really I should have 4, but the reason is because -2 occurs twice. So it's like having -4, -2, 1, and then -2 again. Okay, so the bottom line is that's all of them. That's all the zeros. Okay, so armed with these 3 zeros, I can go ahead and make a number line. Okay, so here comes my number line. Okay, let's see. So I've got -4 and -2 and 1. Okay, notice this is a greater than sign, not or equal to. So these are going to be open circles at these boundary points. All right, if this had been or equal to, then I would have filled these in, but it wasn't. Okay, so all I need to do is test a value in each one of these zones and see if these numbers are solutions or not. If they are, I'll draw them in. Okay, so I'm just going to set up a little table to organize my work. Alright, so I need an x value in each one of these zones to test. To the left of -4, I'm just going to use -5. Let's see, between -4 and -2, how about -3? Okay, between -2 and +1, how about 0? And to the right of 1, how about 2? Okay, so basically I'm going to take these values and I'm going to plug them in to this function and see if the function is greater than 0 or not when I plug these values in. Now I could sit here and take -5 and plug it in for all these x's, or I could use a shortcut. Remember that I already have this entire function in my calculator, so I can just use the table feature. Okay, so if I want to see what the value of the function is at -5, in fact I can just start at -5. So at -5, the function has a value of 54. Okay, so 54. So we're trying to see, is this greater than 0 or not? And the answer is yes. So in other words, if I took -5 and I plugged it in to the function, I would get 54. And so I would get 54 is greater than 3, or I'd get 54 is greater than 0. Since that's a true statement, that means -5 is a solution. That means everything in this zone, all of these x values are solutions. So I will show them by drawing an arrow. Let's see, what would I get if I plugged in -3? Well, again, I can just look at the table to see what I would get. If I plugged in -3, I would get -4. Okay, so is -4 greater than 0? No, it is not. So if I plugged in -3, I'd get a false statement, which means -3 is not a solution. So none of these are solutions. So I'm going to leave this empty. Alright, what if I plugged in 0? You know what? It's interesting. We should be able to do this one in our heads, right? If I plugged in 0 for all these x's, all of these terms would cancel out, and I would just have negative 16. Let's see if my calculator agrees. Oh, look, at 0 we have negative 16, just like we thought. Okay, so we're getting negative 16. Is that greater than 0? Well, no, it is not. So I'm going to leave this empty. All right, now I'm going to see what's going on at x equals 2. If I plugged in 2, I will check my calculator. At 2, I've got a value of 96. Is that greater than 0? Why, yes, it is. All right, so that means everything over here in this zone will be a solution. So I'll show that with this arrow. So these blue arrows represent where all the solutions are. So since they're in two parts, I'm going to have to write two intervals. Okay, for this part over here on the left, this is negative infinity to negative 4. Now, because it's an open circle, that means the border point here, negative 4 itself is not included. By using a round parenthesis, that means that the negative 4 is not included. All right, so if this had been a closed circle, I would have made the square bracket. Now I'm just going to put a union symbol. I don't put anything for this because that's an open circle, so that's not anything. But over here, I have another interval that goes from 1 to infinity. Again, because it's an open circle, I use a round parenthesis. Okay, so that is it. This is called interval notation. All right, this is what is meant by interval notation. All right, so this is the most important part. All right, now just for fun, I'd kind of like to glance at the Desmos app and see what was going on here. What did this graph look like? All right, so here I've typed the function into the Desmos graphing calculator, and this is what it looked like. So here's the x-axis right here. So this represents a value of 0, all right? Right on the x-axis is where the function equals 0. But remember, we wanted to know where the function was greater than 0. All right, so the function is greater than 0. See how all of this is less than 0. The only parts that are greater than 0 are these two little branches right here that are sticking up in the air. This is above the x-axis, and this is above the x-axis. So these are the places where the solutions are. So notice this is at negative 4. So everything to the left of negative 4 is a solution. And this over here at positive 1, everything to the right of positive 1. So left of negative 4, right of positive 1, that's where it's above the x-axis, that's where it's greater than 0. Okay, so that's why we had the negative 4 and the positive 1, and the solutions are to the left and to the right. As you were looking at your yeses and nos with the test values, very often it goes every other one. So when you saw that this was a yes, you were probably thinking, okay, this will be a no, this will be a yes, and this will be a no. But then you see that we got 2 no's in a row. Nothing changed at negative 2. And looking at the graph, you can see the reason why is because the graph didn't go through at negative 2, it was a bounce. Making one last connection, this bounce at negative 2, remember what we found out. Negative 2 was a double root. And whenever you have a double, that's when you have a bounce. Okay, that's why there was a bounce at negative 2. All right, let's look at a couple more inequalities. Let's look at number 8. In problem number 8, we have this. Once again, it would be helpful to have 0 on one side. So I am going to subtract x from both sides like this, and I am going to add 5 to both sides like this. Okay, so that is going to give me x to the third power minus 4x squared minus x plus 4 is less than or equal to 0. Okay, so we need the zeros of this function. So I'm going to go ahead and put this in my TI-30XS multiview, and I'm looking for the zeros of the function so I can make that number line. So I hit my table button. I'm going to clear this out. So I need x to the third power minus 4x squared minus x plus 4. Alright, I always start at -10 because it rarely goes beyond that. So I'm scrolling down, I'm looking for zeros on the y side. Alright, so there's 1. I have a 0 at -1. Keep scrolling. I have another one at +1. And I have another one at 4. Okay, now remember, because the degree is 3, there will only be 3 zeros total. And we found all 3 zeros right here on the calculator. So I do not need to do synthetic division or anything like that. So these are all the zeros I need. So I can just go ahead and do the number line immediately. Okay, so here I go. Okay, so here I have -1 and +1 and 4. Okay, so let's do some test values. And I like to make a little table of values, organizing my work. So I need a test value in each zone. By the way, this is or equal to, so these will be closed circles at the boundary points, showing that, because these are the places where it will equal 0, and we want to include or equal to 0, so we're going to fill them in. Okay, now what's happening between these points? So I need an x value over here somewhere, so here's -1, so I could use -2 or -3 or -4, but whatever you want. In between -1 and 1, I'm going to use 0. Well, you can use even a decimal if you want to. In between 1 and 4, you could certainly use 2 or 3, or even 2.9 or 0 or 1.5, but I'm just going to use 2. And I need something to the right of 4, so I'm just going to use 5. So I need to know the value of the function at these numbers. So I could take -2 and I could plug it in for all these x's and see if it's less than or equal to 0. Because that's what I want to know. Is the function less than or equal to 0 or not in every one of these cases? But rather than plugging them in for all the x's, let's just use the table. Alright, I've already got the function typed in. So if I want to know what's happening at -2, for starters, I might as well start at -2. So at -2, the function has a value of -18. So the question is -18 less than or equal to 0? Yes, it is. That means that -2 is a solution, because I got a true statement. which means that all of these values over here will be solutions. So I'm going to draw that in. Okay, what about at 0? At 0, the function has a value of 4. Is 4 less than or equal to 0? No. So I'm going to leave that empty. What about at 2? At 2, I got -6. Is that less than or equal to 0? Yes. So that means 2 is a solution, which means all of these values are going to be solutions. What about at 5? At 5, the function has a value of 24. Is 24 less than or equal to 0? Of course not. So that means these will not be solutions. So this graph represents all the solutions I'm going to have. And now it's time to write interval notation. So this part is going to be -infinity to -1. And I will put a square bracket because this is a closed circle. Square bracket means we're going to include the borderline point here. And I'm going to put union because I have more than one interval. And now here I'm going to do 1 to 4. Again, closed circles, we use brackets to show that we're including 1 and 4. Okay, so there's your answer in green. This is the minimum amount of work that we want to see. Alright, that was number 8. Alright, let's do one more problem. Number 9. Alright, so I'm going to solve this little inequality as well. Now this one is factorable. Alright, this is the difference of two squares. So that's going to factor as x squared plus 1 times x squared minus 1. Alright, this is the difference of two squares. So x squared plus 1, x squared minus 1 is greater than or equal to 0. Now one of these can be factored more. Can you guess which one it is? Yeah, it's the one with the minus. So the x squared plus 1 can't do anything with that, so I'm going to leave that x squared plus 1. You can't factor the sum of two squares, only the difference of two squares. So this is going to factor as x plus 1 times x minus 1 is greater than or equal to 0. So I've got these three factors, but I'm looking for the zeros. So I can get that by setting each of these equal to 0. Now, when I set the x squared plus 1 equal to 0, subtracting 1 from both sides gives me x squared equals -1. If I take the square root of both sides, I have x is equal to plus or minus the square root of -1. Of course, when you have a negative under the radical, that's I. So this is plus or minus I. Now, you can't graph I on this kind of a number line. So these blue solutions are not going to show up. So it's only the reddish pink ones that we're going to have. So, you know, if I set x plus 1 equal to 0, I get x equals -1. If I set x minus 1 equals to 0, then I have x equals 1. So x equals -1 and x equals 1. Alright, so that's what will go on our number line. Okay, so here's -1 and here is 1. Alright, I'm going to make this little chart to keep me organized. Alright, to the left of -1, I'm going to pick a value. I'll just pick -2. To the right, well, between -1 and +1 is 0, so I'm going to pick that for sure. And over here to the right of 1, is 2, for example. I could have done 3 or 4, but I'm just going to do 2. So I need to check each one of these values and basically plug them into the function and see if the function is going to be greater than or equal to 0. Now, these are the zeros of the function. So I know at, I'm sorry, that's false. -1 and +1, these are the zeros of the function. So at -1, I already know that it's equal to 0. So I'm going to put a closed circle to include that in my solution set. Okay, and this as well, all right, because that's where it's equal to 0. So now what about between the points though? So at -2, okay, now I really could do this by hand. I mean, I could put this in my calculator again, but this is so simple. If I plug in -2 right now, then that would make -2 to the 4th power minus 1 is greater than or equal to 0. -2 to the 4th power is positive 16. Okay, 16 minus 1 is 15. So I'm getting 15 is greater than or equal to 0. Is this a true statement? Well, yes, it is. That's true. That means -2 is a solution, which means everything in this zone is going to be a solution. All right, now if you found that math hard at all, again, I could use the table feature of my calculator and type in x to the 4th power minus 1. And if I want to see what's happening at -2, I can just start at -2. And at -2, I have 15, which is the same thing as I got when I plugged it in by hand. So similarly, if I take 0 and I plug it in, all right, I really should be able to do this by hand, yeah? If I take 0 and plug it in, that's going to give me 0 to the 4th power minus 1 is greater than or equal to 0. 0 to the 4th power is 0. So that's just -1 is greater than or equal to 0. All right? No, it's not. So 0 is not a solution because it gives me a false statement. So none of these are solutions. Well, what if I put in +2? Okay, well that's going to be just like what I had before. All right, if I put in +2 to the 4th power, again that's going to be positive 16 minus 1. Again, that's going to be 15. Okay, is that a true statement? Yeah, just like it was before, yes. So that means 2 is a solution, which means everything over here is going to be a solution. Okay, so this is a graph of my solution set. In interval notation, what I have is -infinity, okay, to -1. This will get a nice square bracket. Infinities are always round parentheses. And then I'll go union, and this is 1 to infinity. All right, and that's it. All right, when I talk about interval notation, I'm talking about this. Okay, so that was number 9.